I was going to talk about the CP2K project, and in particular on the electronic structure module QuickStep today. So what this is about, so the general overview is, as a CP2K is a very large programming package, like many other electronic structure codes. It allows for doing the regular energy and structure optimization. It has a lot of functionality to optimize minimum energy path. And you can also compute a large variety of different properties, including properties requiring the all-electron wave function reconstruction. The general scheme is that beside having static calculations, you can also have all sorts of sampling techniques. So it's a fully fledged MD, Monte Carlo code. You have also all sorts of path integral methods. There's real-time time-dependent density function theory, errant first dynamics for electron dynamics, and you also have metadynamics and other accelerated dynamics techniques. And all of those can be mixed with energy and force methods, and there's quite a large variety of them, going from fully all-electron calculations using the so-called Gaussian augmented plane wave approach. The main driving force is doing pseudopotential calculations using the mixed Gaussian plane wave approach. There's recent development using all sorts of very accurate post-Hartree-Fock methods, random phase approximation, MP2, GW, and for most of them, we have also nuclear gradients, and we can also do this throughout the periodic boundary conditions. There's density function theory methods and Hartree-Fock, like exact exchange and constraint DFT techniques. Very recently, there's also these beta-type neural network potentials. Unfortunately, this is so far still not in the public version. And I also I'm not going to talk about this today anyhow. And there's also great additions in terms of approximate schemes like semi-empiric techniques. And there's also fully MD code inside. I mean, it's not as fast as the LUMS code, but it's actually a fully fledged MD code, which is also inside, able to do all sorts of force fields, charm, Ember, and so on, and having a very well-developed evolved summation electrostatics, which is hardware accelerated by means of GPU and recently also by field programmable gate arrays. And the reason why we have this is that we have all sorts of embedding techniques, QMM, implicit solvation, and density function theory embedding. So basically, that's what I look now at CP2K, because it has all sorts of functionality. So it's not a standard, simple, let's say, Swiss Army knife. It's really the full-fledged version out of it, and it's open source. And according at this website, you have some more information, and you can download this for free. So recent developments mainly concerns large-scale computational kernels. So there's now a fully functional plane wave-based DFT code in form of the Sirius module inside CP2K. As said, there's all sorts of post-Hartree-Fock developments ongoing, and also, and this is most of the thing what we are doing here in Paderborn, are so-called highly efficient linear scaling algorithms to really go to very large system sizes. And we are also working on these second-generation Parallel schemes for quite some years now. And recently also to combine that with proximate computing, so really exploiting hardware acceleration and exploiting the fact that you can make approximate computing and by a modified Langevin equation still be able to recover exactly ensemble averages. There's it's pretty great parallelism. You can have MPI, OpenMP, you can mix that, and there's hardware acceleration. And there's now a full, pretty large library for doing sparse matrix algebra in order to make this very efficient calculation possible. And as said, it's an open source project consisting of a couple of groups. It's mainly my group, and nowadays a group of Yukuta and Zurich, and a couple of smaller contributions from smaller groups. And we have at the moment 2 million lines of active code, and there's all sort of automatic testing happening whenever you contribute, and you can contribute, and you're invited to contribute via GitHub if you would like to contribute some development. So what I'm mainly talking about is the main engine, which is the DFT part, which is the so-called QuickStep code. This is the implementation of the so-called Gaussian plane wave approach, and this is a combination of Gaussian type orbitals to represent the cone-charm orbitals. And we are also making use of an auxiliary plane wave basis for the electronic charge, in particular to allow for periodic calculations. And this really allows for CP2K to do electronic structure calculations and ab initio MD calculation for all sorts of systems, starting from gas phase to molecular systems up to liquid and condensate phase systems. So you can do all sorts of periodic boundary condition as you wish to do. So as said, it's a mixed Gaussian plane wave approach. So the primary basis is a Gaussian basis set, which is quite common in quantum chemistry. And the reason is that you have a very compact representation of the basis set. You have a very intuitive chemical picture of your system, and you can very nicely describe the wave function close to the nuclear cores. It has no implicit periodicity, so this makes it tough to implement periodic boundary condition, but makes it very simple to make calculation in the gas phase. They are non-orthogonal and they depend on the atomic positions. This makes life a little bit more cumbersome, but is reasonably well understood how to deal with that. And there's also basis set superposition error. And the problem, or I wouldn't say problem, but many people are claiming there may be a small problem, is that they cannot so easily systematically improve, and you can run into overcompleteness problem, causing that it's very hard to converge such sort of calculations. So at the same time, we also making use of plane wave bases. They are very orthogonal, so their strengths are compensating for the weaknesses of the Gaussian basis set. They are orthogonal, they have no Poulet and basis set superposition error, and they can be systematically improved quite nicely with a scalar quantity, which is a cutoff. They have, because they are Bloch functions, this implicit periodicity, but on the other hand, it is hard to basically make isolated calculations, and there's a huge number of basis function needed, which makes them not so efficient or less efficient than Gaussian functions, and pseudopotentials are needed in order to describe the quickly varying wave function close to the nuclei. So this is now the energy functional as it looks like. So it has the typical terms, kinetic energy and the potential, including the pseudopotential, the Hartree electron-electron interaction, as well as the exchange and correlation potential. And the idea is to use as for each of these terms the basis representation which is best. So the primary basis, which are the Gaussian functions, are used for the kinetic energy as well as for the external potential. But for the electron-electron interaction in terms of the Hartree potential, as well as for the exchange and correlation potential, both within periodic boundary condition, we make use of plane waves, because in the plane wave community, it's well known how to compute the Hartree potential efficiently in periodic boundary condition, which is very hard to do using Gaussian functions. So this is basically what I've already said. So Gaussian functions are good because many of these things are analytic. That's all the stuff shown here in green, and they can be calculated very efficiently. The Coulomb potential for the two-center electron repulsion integrals in the Hartree part can also be done analytically, but as you will see later, this is the CPU and also memory bottleneck if you're making large calculations, and all the integrations and the exchange and correlation energy are computed numerically. So I will demonstrate that here in particular for the Hartree potential, because as said, this is very hard to compute in periodic boundary conditions. And in Cone-Sham DFT, we even try to avoid completely the calculation of these electronic repulsion integrals. And the idea here is to combine all sorts of electrostatic energy terms into a single one. So we have the electron-electron interaction, the electron-core interaction, and the ion-ion interaction. And so how this is done, and I guess this is the major principle underlying the QuickStep module, is to define a so-called total charge density, which is made of the electronic charge plus the sum of Gaussian atomic charges. And this gives rise to then this total charge density. And the idea is that based on these Gaussian atomic charges, you define a fully fictitious auxiliary potential, which you add and you subtract to the long-range electrostatic interaction. And the reason why you do that is that if you have the electrostatic interaction and you subtract these auxiliary core potential, you end up with short-range potentials. And this is what you see in here in line 2 and 3, the so-called short-range overlap types terms for the electron nuclear and the nuclear-nuclear interaction. So they are now short-range. You obviously have to add the auxiliary potential, which is long range itself, but this is added to the Hartree potential. And so you end up with a modified Hartree potential based on this total charge density, from which you only have to subtract the self-interaction term to avoid double counting. So that means that except of the blue term, the long-range Hartree term, all of the other terms are now becoming short range by that trick and are quite simple to compute. So the reason now is, how can you compute the Hartree potential in periodic boundary condition efficiently? And basically, we are then resorting to plane waves, and we are making use of all the tricks which are available there. So here in red, we have in real space the density matrix. We collocate them onto a regular grid. In real space, we make a Fourier transform, getting in reciprocal space, and then we can compute the now modified Hartree potential simply by summing over all the grid points, and then doing inverse Fourier transform to getting the Hartree potential back in real space. And on top, we can make use of all sorts of efficient screening techniques to make this even more efficient. And the time limiting step here is the fast Fourier transform, which is an n log n step. So this is what you see here. So here on the left-hand side, we have the collocation on the grid in real space. Then we make a Fourier transform and getting a reciprocal space. And here, what you see on the left-hand side, these are the Gaussian exponents, and they come in bunches. Some of them are very quickly decaying, and some of them are smoothly varying. And so here we're making heavily use of multigrid techniques, where we compute each of these on the particular fast real space grid, where this is most efficient. And then eventually getting the accuracy of the finest grid for the full Hartree potential. And this really allows to minimize or to shift the heavy part of the calculation to very coarse grids, and then simply prolonging the calculation from to finer and finer grids, but having smaller and smaller workloads to do. And this is obviously an approximation, and the question is how accurate this is. So here, what we see here is on the left-hand side is EPS default. This is the some default value for the accuracy of the numerical integration. We have, similar to a plane wave code, we have a cutoff. But the important part here is we are not converging to the complete basis set limit, but only to the finite basis, to the finite primary Gaussian basis. And so you see, when you increase the cutoff, the calculation on the right-hand side becomes more and more accurate. For example, you see here at 800 Rydbergs, so you get a very, very accurate number already, which is very close to the reference number, but the corresponding computational time is rather large if you're having a single super fine grid at these 800 Rydbergs. So if you're now making use of multigrid techniques, so here we have 4 and here we have 6, what you see is the time is now increased by a factor of 25 in that particular case, and you see you can now compute the Hartree potential still within very, very great accuracy with the fully converged calculation on a very, very fine grid. As said, since the primary basis now is a Gaussian basis set, we have a so-called basis set superposition error. And this is what we see in here. So this is now for liquid water, for different configurations, for different basis set sizes. And you see here is the larger the basis set becomes, the smaller the basis set superposition error becomes. And even for the largest system, basis set superposition error is still present. However, since we are mainly interested in dynamics, we are more interested in the spread rather than the absolute deviation from the exact Born-Oppenheimer surface. And what you see here is that even at reasonable small basis sets, so here, for example, for the triple zeta, the spread is rather small because this affects energy differences and eventually nuclear forces. And this allows to compute even with reasonable small basis sets very efficiently systems, energies and forces in a Conan space, and allowing to do very accurate molecular dynamics simulations. So now we have shown how we can combine the efficiency, and I will elaborate on this shortly, of the compact representation of Gaussian functions, together how we can deal with periodic boundary condition by taking the detour over plane waves. So this is good for doing a periodic calculation, as I've just shown, but the problem is if you want to make isolated calculation, because now we are computing the Hartree potential similar to a plane wave code strictly in periodic boundary conditions. And so we need to solve the Poisson equation now for non-periodic boundary conditions, and we then have similar techniques then are well known in the plane wave world, in the CPMD codes and in QuickStep and some others implemented in order to reduce now the periodicity from 3D to 2, 1, and 0D for doing gas phase calculations. So recent developments now going is mainly dedicated, beside going faster, is going to doing more accurate calculation, in particular is reference calculations for training these neural network potentials, as we've heard. So what we are now doing a lot since a couple of years are computing the Hartree-Fock Exchange. And for those of you who have heard about these things, these are very, very expensive to compute, because here, what you see here is you have 2 electron or force center integrals. So this is now here a 4-fold loop. And these are very long loop, and this makes these calculations, if you do trivially, about 2 orders of magnitude more complicated. And these density fitting techniques, which are well known in the quantum chemistry world, are not so helpful here in periodic boundary condition using this Gaussian and plane wave approach. And furthermore, we also want to do everything strictly in periodic boundary conditions. So this is adding a lot of additional complications, because many of these very slowly decaying 1/r-like terms are overlapping over periodic boundary conditions. And this leads to a lot of huge numbers of integrals which needs to be calculated. And this causes also a couple of stability problems. And we also want to have these Hartree-Fock code to be stable for large basis sets. So it's not a trivial implementation, but let's say in a direct implementation, we already make use of a couple of tricks, which is well known. First of all, we are using truncated Coulomb operators. So this is this complementary error function here, or these short range hybrids, where you have the 1/r term only for distances smaller than a certain radius and 0 otherwise. And this really makes these calculations stable in periodic boundary conditions. Really great help are the so-called integral screening. So this is now here the Schwarz inequality, and this allows you to a posteriori estimate if it is necessary to compute the integral at all. And this really allows to make linear scaling Hartree-Fock exchange calculations. And moreover, we are using integral compression. This is a fully exact compression scheme, particularly suited for these integrals. And this really allows to having to compress these integrals before storing them into memory at a compression rate between 6, 7 up to a factor of 10 without any approximation. And this allows really to keep all the integrals in memory without having to resort to your hard disk. And even using these ideas, you can see here, you can make in periodic boundary conditions with an all electron basis set, pretty sizable calculation. They are not cheap. Yeah? You see these are thousands of basis functions here, and you need billions of integrals what you need to compute, and you need gigabytes, and in worst case, even terabytes of memory to store all these integrals, which requires quite sizable computation resources also in terms of memory. Here with the in-core compression, we have here throughout a factor of 8 without any approximation. And this is now the timing what you have. So if you have sufficiently large computers, you can make hybrid DFT calculations using that implementation with sizable resources already, and can do even dynamics and Monte Carlo sampling if you wish to do so.
So 20 minutes.
However,
minutes remaining.
Yeah, okay. Also, if you really would like to make very efficient, a more efficient calculation, so there's now quite a good idea and have some tremendous savings is that you have now a so-called auxiliary density matrix for which the computation of the exact Hartree-Fock exchange is much more efficient. So this is here the matrix D. So here you compute the exact exchange basically on a much smaller matrix with great efficiency. And then you are projecting from the approximate matrix D to the exact density matrix P, but you only do the projection, here as the correction terms, at the GGA level, which is then comparison to exact exchange basically nearly for free to compute. Yeah, and this really gives you a great additional savings in order to do these hybrid DFT calculations. And that's what you see here. So here with 256 CPUs, this is now a pretty sizable system with nearly 4,000 electrons, periodic boundary conditions, 23,000 basis functions. And if you really do a conventional GGA calculation, you need 230 seconds for the initialization. And for an SCF step, you need 120 seconds. And using this auxiliary density matrix approach, which I've just shown you, you can make B3lib calculation. That means the same stuff, just adding Hartree-Fock exchange at an additional cost, which is about a factor to 2 to 4 times more expensive than already a very efficient GGA calculation. And since there are so many integrals to compute, you can obviously, these calculation scales quite well because there's all these billions of integrals what needs to be computed, and they can be very nicely distributed over very large numbers of cores. And so you can make with larger numbers of CPUs calculations at the speed of a GGA calculation if you have sufficiently large computation resources available. Question is this exact? And this is here what you see here. So this is a PB0 calculation. This is now the band gap. So here in exact, if you make this initial implementation, that's what you see here. You get this corresponding number for the band gap, but these are now millions, billions, 40 trillions of integrals, what you need to compute it. And this can be now reduced to 24 billion of calculation. This is a tremendous savings. And you see the estimate what you get out for the band gap is nearly not affected. So the approximation here is rather small, and the gain efficiency is huge. There's, as said, all sorts of post-Hartree-Fock methods implemented, including for most of them forces, except of GW. And we can throughout the work for periboundary conditions. And there's all sorts of very, very sophisticated tricks based on the resolution of identity to reduce the scaling. And you can also now compute, you can in some cases even do Monte Carlo sampling using these very, very sophisticated post-Hartree-Fock methods. Unfortunately, for the time being, only at the gamma point. And this is one example. So this is now an NPT sampling, Monte Carlo, by colleagues of mine in Zurich. So this is now 64 water molecules. This is now a couple of years old, but this is still, I would say, state-of-the-art calculation. So you have about 200 atoms. And so what they have done is they have now done regular GGA calculation. Takes about 100,000 CPU cores. A PB0 calculation takes about 3 times as much effort using the auxiliary density matrix method. Using it in an efficient but direct approach, it is about 20 times more expensive. Using doubly hybrid with our latest and greatest cubic scaling random phase approximation code is about 60 times more expensive. It's nearly 100 times more expensive using RPA with resolution of identity throughout, which is a cubic scaling code. And if you make everything in a resolution of identity, MP2, which is n to the 5th, it costs you about 15 million. And so what they have done is they have, for example, did quite a tremendous numbers of Monte Carlo cycles. And they had been interested in computing the average density of liquid water, which is known to be very hard to compute using conventional density function theory. And this is also needs huge numbers of samplings in order to converge these numbers, but using this efficient implementation, this is now possible. And you see this systematically improves the quality of conventional DFT calculations. And our hope is that this may be, for example, of interest to that community, to use that to include this to parameterize these neural network potentials. So how I'm doing with the time?
You're at 5 minutes, so if you can wrap up really quickly, that'll be good.
Okay, so okay, so we have the conventional eigenvalue solvers as every code, so this is nothing new here. We have also very efficient direct minimization techniques for going to large-scale systems. And this is still, I think I show it here, this is eventually, this is all of these, you have now very efficient Cohen-Char matrix built up, and M log n. Then you have these density matrices, even if they are not sparse. This is, all of these terms are linear with the numbers of basis functions, but eventually even these very efficient minimization schemes are cubic scaling because you have to multiply it in square. And here, this is now, forget about the numbers, this is now a 10-year-old calculation, but you see in the beginning, even using these very, very efficient but still cubic solving eigenvalue solver, we are nearly linear scaling. But if you're going now up in system size, eventually the eigenvalue problem becomes dominating. And you see here at the beginning is 14% linear algebra. That's why we have the nearly linear scaling. And for the larger system, we have about 67% linear algebra, which is why we had been heavily working on recent years. And this was partially done with quite tremendous support from my group and also from the Compute Center here in Paderborn, is to go to linear scaling. So we are making use of what is known as the sign method. This is a very ancient technique, but the good idea here is that eventually the only thing what you have to do are multiplications of very large but sparse matrix multiplications. And so this becomes now a computer science problem. And then we have a lot of people inside the community, including us, have then developed the so-called sparse matrix multiplication library, which in itself is now hundreds of thousands of lines big library. And this really allows now to go to huge systems with linear scaling. And I think this is the last plot I'm going to show. Mm-hmm. So here in the red curves, we have conventional Cohen-Char DFT. And so this is now with a reasonable accurate basis set, a double zeta. And here you can go, let's say, to what's that? Hundreds of thousands of atoms with great resources. So here we're talking about 50,000 cores. But if you're now going to essentially minimal basis set, and there's now even a machine learning technique where you can on the fly learn minimal basis sets, which are still very accurate, you can go up to million atoms, full DFT calculations. And if you're now happy with semi-empirics, you can make these calculations even in a multi-million regime with much smaller computation resources possible within the corresponding approximations. And with that, I would like to stop.